Hi, and welcome to Dr. V's AP Chemistry podcast. Today we're talking about the common ion effect, and we're going to go on and talk about how we can use this to predict if a precipitate will form when two solutions are combined. So what I'd like to do in this webcast is explain the common ion effect and what it does to the solubility of slightly soluble salts. We'll use ice tables to solve problems, and we'll use Qsp, the reaction quotient, to determine whether a precipitate will form if we combine two solutions that could potentially form an insoluble product. So let's start with this idea of the common ion effect. What's going to happen to the concentrations if we add a salt that also contains an ion that's part of the equilibrium? Well, here's the thing, it's really Le Chatelier's principle. Here it is very formally. The extent of ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion in common with the weak electrolyte. Oh, Lordy, like what does that mean? Here's the gist of it all. If you add a common ion to a solution of a slightly soluble salt, you're going to get less of the salt to dissolve. So let's say we have some poorly soluble salt, AB. It dissociates to form A+ cations and B- anions. And we can write an equilibrium constant for this, right? The products over the reactants, but since the reactant's a solid, we can effectively eliminate that, or just ignore it. Okay, so if we add some other salt, say Xb, right? It's got some other cation that also contains the B- ion. And we put that into solution. We're going to increase the concentration of the B- ion. Well, right, Le Chatelier's principle, if I increase the concentration of products, it's going to shift left to reach equilibrium. Since I increase the concentration of the B- ion, the concentration of the A+ cation must decrease. So I'm going to have less of these ions in solution. Less of the original salt will end up being dissolved because I'll have less A+. That's really what we're trying to get at here. So let's go through and do a practice problem where we have to worry about a common ion. Calculate the molar solubility of barium carbonate in a solution that contains 0.05 molar sodium carbonate, and then conveniently we're given the Qsp, a Kq for the barium carbonate. You'll notice it's a very small number. Okay, so what we're trying to say here is that carbonate, right, it's part of the original thing we're studying, and then we're going to add a salt that also contains carbonate. So that means carbonate is the common ion here. Okay, so that means when we go to set up our ice table, there's already some carbonate in solution before we actually set anything up. With doing these problems, you always want to start with a balanced equation, right? Barium carbonate needs to be the reactant here, right? It's a solid. It will make barium ions and carbonate ions in a 1-to-1 ratio. Next, we need to write out a Qsp expression, all right? And so, right, products over reactants, but the reactant is a solid, so effectively the denominator is 1 here. So we're given the Qsp value. That's equal to the barium ion concentration times the carbonate ion concentration. No problem. All right, so now we can start to set up the ice table. But if we go back and look at that original problem, all right, we didn't have any barium present in the solution, but we did have 0.05 molar carbonate present in the initial solution. And then we're going to add the barium carbonate in. Okay, so we need to know how they change. Well, the barium concentration, there wasn't any, so it's going to increase by X. The carbonate ion concentration is going to increase by the same amount because they're in a 1-to-1 ratio. But of course, we already had some carbonate. So when we look at the equilibrium concentrations, the barium concentration would be X. The carbonate concentration would be 0.5 plus X. Fine. It's a very typical ice problem. Nothing unusual here, really, except that, of course, we had an initial concentration of the carbonate that wasn't 0. But that's okay. All we're saying is we had a common ion. All right? So it turns out, because the Qsp of barium carbonate is so small, right, 10 to the minus 9th, that's really small. We can make an approximation. All right? We can assume that X is much, much less than 0.05 molar. No problem. All right, as long as your Keq, your Ksp is less than 10 to the minus 4th, this is an okay approximation to make. All right, and so we can assume that 0.05 plus X is about 0.05. And because our Ksp is so small, X is going to be less than 5% the original concentration. So this is a reasonable approximation for us to make, and it will make our math much easier. So now we can substitute these values in, all right, and we can simplify it, right, because we said 0.05 plus x is about 0.05. That makes our math really easy. All right, so all I did was take my equilibrium values and put them in. Nothing complicated here at all. And then I'm just going to solve for x. Just doing some really simple math. I just need to effectively divide both sides by 0.05. All right, which gives me a value of x of 1.0 times 10 to the minus 7th. So that means 1.0 times 10 to the minus 7th moles of solid barium carbonate should dissolve per liter of 0.05 molar sodium carbonate solution. Not going to dissolve much, but it's not a very soluble salt. We can see that from the Qsp. Now, as I said, there are other problems that we have to worry about here in terms of the common ion effect. Will mixing two solutions result in a precipitate? It is really an application of this as well. There's still equilibrium problems, so you want to write out a Qsp expression for the expected precipitate. This means you might want to review your solubility rules. We have to calculate the new concentration of the ions involved once we've changed the volume. We've mixed these two solutions together. Their initial concentrations have changed. You do normally need to make the assumption that the volumes are additive, although the problem should mention that. Then we're going to substitute these concentrations into our Qsp expression to calculate Q. All right, you can call it a Qsp, but it's really just the reaction quotient for this type of system. All right, if Q turns out to be greater than K, all right, meaning you have too many products, too many ions in solution, it's going to shift left and a precipitate will form until those equalize and you reach equilibrium. If Q is less than K, you don't have enough ions in solution, you can shift to the right and that means no precipitate will form. And that's really something you need to be able to do. These problems are important. All right, so let's look at this problem. Suppose 100 mils of a 0.02 molar NaCl solution are added to 50 mils of a 0.01 molar silver nitrate solution. Will a precipitate form? The Qsp of silver chloride is given 1.78 times 10 to the minus 10. And then we're nicely told, assume the volumes are additive. All right, so really the key here is to write out the Qsp expression. We've got this problem. There's a lot going on here, all right? But you hopefully know that if you mix NaCl with AgNO3, a double displacement reaction will occur, and we're going to make silver chloride as the expected precipitate. If a precipitate forms, it would be silver chloride. So when we go to write our Qsp expression, we're going to do it in terms of the silver chloride. All right, so a balanced equation here is very handy. Remember, your solid would be the reactant. The silver ions and the chloride ions would be in a 1-to-1 ratio. And we'll write our Qsp expression, and we know the value is 1.78 times 10 to the negative 10. Fine. We're going to need this, so just sort of set it aside, and we'll come back to it in a moment. The next thing we need to do is calculate the new molarities. All right. We had 100 mils of the first solution and 50 mils of the second solution. So that means the new volume is 150 mils. Well, really, it's 150.0. Well, 150 mils. So we know that to 3 sig figs. So let's do it for the chloride first. We can just use M1V1 equals M2V2. The moles of chloride are the same. The concentration will change. So we can just rearrange the molarity formula to get this. All right, so we can solve for N2 essentially. We knew the initial molarity, the initial volume of the chloride. We know the final volume of the solution before equilibrium occurred. We're calculating the new molarity of the chloride. It works out to be 0.0133 molar. Great. Let's do the same thing for the silver ion. Okay, still 150 mils. All right, same process. M1V1 equals M2V2. So we had 50 mils of a 0.01 molar solution. The final volume is 150 mils. We're calculating the new molarity. We get 0.00333 molar. All right, sometimes when you do these problems, you'll be mixing equal volumes, and then it's easy. You can just have the molarities, but it's not always going to be the case. So I chose a problem that was a little bit more involved. All right, so now we can substitute these new initial concentrations into the Qsp expression. All right, we're going to call it Q because it's our reaction quotient. what's the ratio of ions right now? All right, so we're going to substitute in the silver ion concentration, multiply it by the chloride ion concentration. We get a value of 4.43 times 10 to the minus fifth. That's the current Q. All right, well, our last step is to compare Q to K. We're given K, we were just finding Q, and it should be obvious to you, just looking at the exponents, right, that Q is much larger than K. All right, so it's the times 10 to the whatever that really makes the difference here. Q is much larger than K, and therefore we can conclude that a precipitate will form when these solutions are mixed. Wonderful. It's always good to be able to do these very important problems.